Prego, buongiorno. Entrate pure, disponetevi magari un pochino distanziati.
sentite?
Sì, un attimo solo. Allora, ok, direi che siamo pronti per partire. Moreno, se vuoi iniziare anche con lo streaming. Allora, buongiorno a tutti, scusate questo lieve ritardo, ma penso che servirà a recuperare qualche minuto durante la strada. Benvenuti a tutti quanti, benvenuti ai candidati e alle famiglie. È una bella giornata. Andiamo a ascoltare i nostri studenti un'ultima volta nella loro presentazione. Cominciamo con il signor Alex Aglietta, che ci presenta una tesi di laurea magistrale dal titolo Feasibility Study and Validation of a Spool Position Sensor Detecting Method for Solenoidal Valves. Come sapete, il corso di laurea magistrale in Electronic Engineering è completamente tenuto in lingua inglese, quindi le presentazioni dei ragazzi saranno tenute tutte in lingua inglese. Signora Aglietta, prego, la parola a lei.
So, hello everyone, I'm Alex Aglietta, and today I will present my thesis study did during the internship into Bosch Rexroth Oil Control Company. I did a feasibility study and validation of a spool position sensor detecting method for solenoidal valves. So the keywords of the study are size, cost, smart software algorithm, and safety. And I was looking for a new device with smaller size than before and with low production cost. Also, this device must integrate a smart software algorithm able to find the position of a spool inside an hydraulic valves in a safety way and also in a faster way than before. So also the other objectives of the study are to find a new procedure in order to the characterization of the hydraulic valves and also to find a first development step for algorithm insertion into a control unit. So my study will connect the initial study carried out from the research center of Bosch to the end customers' needs. And in order to do that, I started from a theoretical analysis and from a Faraday-Newman law, studying this equation, this law. This equation allows us to find the induction into a coil with respect to the position of the plunger inside the coil, and also with respect to the current circulating to the coil. And I studied also that there is a relationship between these two parameters, and it is that for every 0.1 millimeter of displacement, there are 1.3 milliampere of change in current. The current into the coil was read using a digital sensor. This is a Texas Instrument chip, and it is integrated into the electronic board, and it is the most suitable way in order to find the current for our purposes. Then the core of the study is that diagram flow, which explains the algorithm used in order to find the spool position of the hydraulic valves. And starting from a self-fitting process, an acquisition string could be found. And then after a check, in order to understand the type of the valve tested, with mathematical process and MATLAB software, the final position of the spool could be found. And then if the position is, for example, of a normally closed valve, is higher than the threshold level, so the algorithm must send information at the other system electronics because there are no longer safety conditions. In this case, the valve is open when it must be closed. In particular, the software takes 5 different current periods and analyzing it using some function of MATLAB, for example, linear poly. And using this function, the most important parameters in order to find the spool position will be found. For example, also here X and Y, or also alpha and beta. In the second image are shown 5 different hydraulic valves. Each of these valves has a different gap position. And using these parameters, the different positions are easily recognizable. Then the characterization test used in order to find the optimal parameters from the hydraulic valves is the thermal cycle test. This is also the old procedure used. It has a great advantage of have the goal to find very good parameters for the end position measurement, but also has a great issue, and it is its duration of about 2 hours of every singular gap position tested of the valves. And so my goal was to find a new, faster procedure, but at the same time able to find very good parameters which can stay within a tolerance range for the final position measurement. This is the so-called self-heating test. It acts on the PWM excitation on the valve, on the coil, and changing the duty of this excitation, also the current inside the coil changes. And then with the initial current measurement, good parameters will be found. And then using the algorithm, the position of the spool could be found. Also, the end customer can use this test because its duration is lower than 5 minutes. And so definitely a great goal was achieved using this test. In order to see the goodness of what I've studied, I did this test. This is the test setup of the reading of the spool position. And the hydraulic valve was connected to different type of measurements. The first one is using the studied sensor as board, and so also the algorithm studied. The second one instead is using an external laser sensor, in this case a micro epsilon laser sensor. And the spool of the valve will be moved manually using the manual pusher, which is represented in the figure. And then the results are shown in this video. I can't. But it's a video where the detecting position is moving in this okay, and then the same measure was exploited also using the laser sensor. And here the two measurements are very close between them. And also the measure obtained using the MATLAB GUI stay within a range of 10% of tolerance with respect to the reference one. So also here it's possible to see a very good result of the study. Oh, this is the video. Okay. And here the positions are practically identical, the two positions. So it means that the result is acceptable. Okay. Then other test is carried out using the old procedure, and so this is the measurement of 5 different gaps into 5 different valves, using the old procedure for the characterization parameters, and so that is the reference measurement. And on the right, instead, there is the measurement using the study algorithm, and so the new procedure, the much faster procedure. And so here, the offset between the two measurements is about of 60 micrometers, and it stays into 100 of micrometers of range. So also here, the result is acceptable. Then, concluding, the feasibility of the project was achieved, and also using a smart software algorithm and a new procedure for characterization test, it's possible to find the position of the spool with good precision and in a very fast way. Also, the basic electronics used is not very expensive, and in progress there is the development of a new software able to be usable also for a microcontroller. Thank you.
Okay, thank you for the presentation.
Thank you.
Any question from the jury?
So, which are the specific or best applications for this kind of position measurements?
Could be a lot, because this device could be inserted into a microcontroller. So, for example, in Rexroth there is the CHC controller, which can play on the move of some machinery. And so if we want to see the safety, for example, to 1 valves, we can do it with that software, because it can measure the position of that valves.
But do you have in mind some specific applications where this position measurement is very critical?
So, for example, in a telehandler application, could be one way to use.
Okay. Any other question? Just curiosity, you mentioned delta error of 10%, but the curves that you showed were actually seem to be much better than that. So in which case, I guess you did more tests?
Yes, a lot.
What was the most demanding one, the one where you found the biggest error?
So, for example, in the case of maybe a great change of temperature in a low time, it's possible to see different parameters, and so the range of the measurement could be outside the 100 micrometers or 10% of tolerance.
Okay.
Thank you.
Okay, very good. Thank you.
Thank you.
Okay, so. Okay, so now we have
qubit theory, we have different states we have. So the importance like qubit theory, we have different states we have. So and because of that we have so many importance like qubit theory, we have different states we have. So because of that we have so many importance like qubit theory, we have different states we have. So because of that we have so many importance.
So next one, we are going through the quantum mechanics and principles. First, the conjugate pair of the subatomic particles. The quantum pair of the conjugate pair of the subatomic particles. The quantum pair of the
Ali, just a second, there is a technical problem. Stop. We hear you a lot of echo.
Yes, yes.
Just a second, there is a technical problem. Ali, you can start again. Ali, please.
Okay,
Please continue.
now we are going to the quantum mechanics and principle. The first principle is simple.
Ali, you can start again. Ali, please.
Again from the first.
Please continue.
Now we are going to the quantum mechanics and principle. The first principle is simple.
Ali, you can start again. Ali, please.
Again from the first.
Please continue.
Now we are going to the quantum mechanics and principle. The first principle is simple. We are going to discuss because in the recently understood the conjugate pair of the next slide we are going to describe the quantum bits. In quantum bits, first we have to know about the classical bits. Classical binary, we have only two deadly state, one and zero, and cryogenic CMOS control for it is not possible in practical because it has it managing the thermal circuit is very difficult. In the other hand, controlling it is not possible in the other hand the controlling it managing the thermal circuit is very difficult. In the other hand, controlling it is not possible in the
And we can switch off this. We can switch off this. So please come to the stage, and the title of your thesis is HIL Simulator of Hydrogen Fuel Cell Vehicles. Please, the stage is yours.
Prova. No, scusate un attimo. Okay. So, good afternoon to everyone. This thesis was done with pure power control and analyze an hill simulator for hydrogen fuel cell vehicle. Model-based design is a methodology based on a workflow known as the V-diagram. This is a mathematical and graphical method and is used when addressing the design of a complex system. Basically, 4 steps are necessary during the process. The first one is to build a model of the plant, then analyze the plant and synthesize a controller, then simulate them together, and at the end deploy the controller itself. This thesis has the scope to demonstrate the effectiveness of hardware-in-the-loop simulation system used for testing and validating the control algorithm used for a hydrogen tractor. The proposed powertrain architecture is shown in figure, and it comprises 3 electric motors, an onboard fuel cell, lithium-ion battery. The two of the 3 motors are mounted on the front axle, each one with its own reduction gear, while the rear axle, we have the rear motor coupled with a power shift transmission. Electric vehicles have many advantages over classical vehicle with internal combustion engine, such as the absence of pollution and quick refueling time. Electric vehicles are better than classical vehicles because we have many advantages. But also on the advantage, we have also some disadvantages, such as very long recharging time for the battery and limited driving autonomy. So to overcome this issue, the idea is to place a fuel cell on the vehicle, and the architecture is shown in the lower figure, where the fuel cell is connected to the inverter through a boost DC-DC converter. The battery pack instead is connected directly to the inverter. It's not possible better. One can use only the fuel cell, but then the vehicle would present very poor dynamic response. So in order to improve the drivability of the vehicle, a short storage system is required, such as a battery pack or a supercapacitor. Fuel cells are electrochemical devices that convert chemical energy into electricity. The hydrogen gas has a very high energy per unit of mass. But on the other side, for low volume, it has a low energy density. So this is the reason why the hydrogen is stacked in special tanks with very high pressure. The output voltage of a single cell is approximately 0.8 volt. And therefore, as the cells are stacked in series to obtain higher voltages. During the process, the hydrogen is it's fed to the anode, while the oxygen is fed to the cathode. And this, in particular, this case, we have a proton exchange membrane fuel cell, also known with the acronym of PEM. At the anode, when the hydrogens interact with the catalyst, it dissociates into electrons and protons. But due to the presence of the membrane, the electron cannot travel directly to the cathode, so they have to take an external path, while the proton can travel and reach the cathode. On the cathode side, electrons from the external side, protons and oxygen, combine and form water. In order to simulate the behavior of the tractor, both lateral and longitudinal dynamics have been considered. In particular, the longitudinal dynamics considers that all the force acting on the longitudinal direction are equal to the mass of the vehicle times the acceleration, where the force are the one between the four wheels and the ground, to which we have to subtract the aerodynamic drag force, and in case of slope road, the gravitational contribution. On the graph below is shown the maximum traction force that the vehicle can generate, considering all-wheel drive configuration. I mean, we are considering the maximum power of the three motors and atypical working conditions such as plowing. The different lines determine a different range of the gears. What's concerning about the lateral dynamic is that the steering mechanism has the highest impact for the maneuverability of the vehicle. And all the relation has been estimated from the mathematical model of the vehicle. A very important role is played by the yaw rate, which is fundamental for the vehicle stability. The traction control algorithm is based on the velocity. This means that when the driver sets the velocity with the accelerator, and independently of the resistive force on the external load, the algorithm provides to the motors the required force to achieve the speed. So considering the powertrain configuration, it's better to think in terms of traction force instead of the torque to the single motors. So after the evaluation of the traction force, this is split between the front axle and the rear axle. At this point, it's converted into torque, and with torque vectoring, it is distributed on the motor. Due to the fact that on the front axle we have two separate motors, each one for one motor for each wheel. The vehicle is able to work in different conditions, such as charging, traction, boosting, and regeneration. During charging, it simulates a refueling of the tank for the hydrogen, a charging of the battery. During traction, the main power is provided by the fuel cell itself. But during boosting, a combination of fuel cell and battery provide the power to the electric motors, while regen emulates a regenerative braking, where the mechanical power is converted into electrical power and used to recharge the battery. Once the control algorithm and the plant has been designed, it's time to simulation and validation. And basically, there are two approaches: software in the loop approach and hardware in the loop approach. A particular case of software in the loop approach is the model in the loop, when the controller and the plant run on the same computational node, and basically they involve any real-time coding. Different story for the hardware-in-the-loop simulation. In this case, a prototype or the real ECU is taken, and the plant is the model of the plant is converted in a C code, and our case was uploaded to a PLC, which was our virtual tractor. The architecture of the simulator composed the real-time simulator, the PLC, the ECU under test, a joystick command, and an external computer. The hardware in the loop, the ECU and the joystick communicate to each other with CAN communication protocol, while the external computer is used to display the vehicle in a virtual environment and a dashboard with some information such as the vehicle speed or the power of the motor, the level of the cell, and so on. There are simulation results. In particular, on the first graph, it simulated that the vehicle go forward, stop, and then go reverse. This used to test the all-wheel drive configuration. This is true because we have torque and speed on both motors. And during the braking condition, we can see that the last graph, the state of charge of the battery increase, meaning that the external power the mechanical power is converted to electrical power and used to recharge the battery. Here there is a short video. If we start. Okay, that show the tractor in the virtual environment with the dashboard modeled in MATLAB GUI, and where are displayed information such as the sock of the battery, the fuel level, the power flow in the powertrain, and also the vehicle speed and the speed in the power of the motors. Thank you for your attention.
Okay, thank you for the presentation. Any question from the jury on this thesis? We have two, actually. Matthias, please. Okay. Then we go to...
So I have just a curiosity, and it is the following one. So what is the lessons that you learned by simulating this special type of alimentation for a tractor?
The system is not only for simulation, but is proposed to test the issue that would be mounted on the real vehicle. So with the simulation, we are able to detect some issue, failure, and stuff like that. So it's such as the hardware in the loop suggests, you have to simulate the prototype to avoid damage on the real vehicle. This is the main idea behind.
That's very clear. But the question is, what is the lessons focused about the kind of energy, fuel that you are using? Because the hardware in the loop, you can also use it for a normal engine. But in your case, in your special case, you are using hydrogen. So the question is, do you receive some special lessons about this?
I mean, hydrogen could be one of the fuel that would be used in the next year. So we try to...
Yes, but my question is that I cannot understand what is the special focus in your work about the use of hydrogen. Or you have just simulated the mechanical behavior of the tractor? We
have simulated the mechanical behavior of the tractor with the power provided by a fuel cell.
Okay, and now
instead of us.
Okay, and did you receive some special lessons about the fuel cell or not?
I mean, is there anything different if instead of having a fuel cell you would have another source of energy? I guess this might be.
Yes, because if I replace with the electrical battery, I believe it's the same for you now.
No, but let's.
No, I'm sorry.
Answer. That's okay. You can keep the discussion for later. There was a question also from...
Luca, just maybe that I missed the point. In your simulation will take in account also temperature effect
Yes,
and
sure.
and also aging of the device. Are you able to take in account aging, different performance due to the aging, for example, of the battery?
Yes, both modeling for the battery and the fuel cell are temperature based. So with the increasing of the temperature, the performance of the battery, we have demonstrated that reduced drastically, and both for the fuel cell.
Okay, also the aging.
Yeah.
Okay.
Yes.
Okay, thank you.
Okay, thank you. There are no other questions. Okay, so let me call to the stage Francesco Gammarotta. And the title of his thesis is Characterization of RTN in FDSOI transistors. So please, Francesco.
It works? Yes. Okay. Okay, good morning to everyone. Today I would like to present my master thesis project named Characterization of Random Telegraph Noise in Full Depleted Silicon On-Insulator Transistor. That is a research project that I started during my Erasmus experience in Spain in collaboration with the Universidad Autónoma de Barcelona. Before to explain what are the main features of this transistor technology, I would like to do a brief list of what are the most CMOS technology downscaling problems that normally we have. In fact, normally downscaling, we have a problem linked to the gate dielectric thickness that sometimes can lead to early breaking down of the device. After we can have a problem linked to the leakage current in our device, in dissipation of heat, and problem as bias temperature instability, which can be manifested, for example, as a carrier channel or random telegraph noise. So let's see what are the main features of the technology that I analyzed. So its particular structure has an ultra-thin buried oxide under the source and drain layer. Thanks to this, we are able to have a huge reduction of leakage current that leads to less power consumption. After we have an undoped channel between the source and the drain that leads to have a high channel mobility, and we have a reduction in parasitic capacitance, and one main feature is the possibility to control the threshold voltage. Normally, we can do this, but in this kind of transistor, thanks to the body biasing technique, we are able to do it, applying a voltage on the body biasing terminal. So, as I told before, what I analyzed is the evolution of random telegraph noise in specific cases. In order to understand the following analysis, I'm going to present what does it mean, random telegraph noise. Okay, this slide helps us to understand. The upper image shows the drain current function of time, and as we can see, there are two main discrete levels. Our current normally jumps from one discrete level to another, depending on the electrons that could be trapped in gate oxide defects. As we can see, once an electron is trapped inside this gate oxide defect, we have a decreasing of the current. Vice versa, we have an increasing. So let's focus now about the step of my research analysis in order to understand the overall process. Okay, at first, my research was focused in finding the smallest and more resilient device that I could analyze. In fact, we know that random telegraph noise is promoted in smaller devices. After we tried with my team we try to understand which could be the stress condition that could promote most interesting results in our analysis. And third, we define more RTN bias configuration in order to see which voltage on the drain and on the gate promote most random telegraph noise during working condition. In order to understand the massive study that has been done during this experience, I would like to say that more than 60 devices has been studied, and normally one test of each single device normally take more than 3 or 4 hours. We tested six stress conditions, and we defined 9 RTN bias configuration in order to see which one promote most RTN. So, to start, I would like to present what was our measurement setup. Mainly, we have 3 stages. The wafer probe station, the semiconductor parameter analyzer, and the MATLAB environment. Normally, the semiconductor parameter analyzer promote the voltage sweep on our device. The wafer probe station allows to the semiconductor parameter analyzer to communicate directly with the terminals of our device. And another feature of this semiconductor parameter analyzer was the possibility to create directly a MATLAB file with all the useful data that we have to analyze. So, as I told before, the first part of our research focused in finding which could be the best, the smallest device enough resilient to analyze. After our analysis, where we stressed our device, we could see that a device with 30 nanometer of width and 40 nanometer of length was enough resilient to support our analysis. Moreover, as I told before, we try to see which could be the best stress condition to apply to our device in order to promote degradation. We didn't want to have a too much soft impact on the device and not a too much high impact on the device. That's the reason why, at the end, we choose as stress condition during our stress cycles gate voltage equal to drain voltage equal to 1.5 volt. So, the main tool that I used during my random telegraph noise analysis is the weighted time-lapse plot. In order to understand how it works, I would like to use the image on the left. On the right, we have the atypical weighted time-lapse plot. On the left, we have one of the principles that can help us to understand how it works. In fact, on the left, we have an image divided into 2 parts. In the first part, we have a typical drain current with a lot of discrete levels. And as we can see, we are able to define which levels of current occurs most, and the level of current that occurs most, we are going to define them as discrete levels. The small step around are going to be defined as noise. Exploiting this kind of analysis, we are able to create the weighted time-lapse plot that I'm going to try to explain in a graphical way. So, analyzing the diagonal of this graph, we are able to see the number of discrete levels that appears during the analysis of the drain current function of time. What we know is that every couple of clouds, we have 2 discrete levels in which my current is jumping. And that's why we define every 2 clouds that we have a jump. As we can see, in the case that I analyzed with this graph, we had 4 discrete levels. So, moving on, I would like to exploit these tables in order to summarize what was my almost overall work in my research. What we can see? As we can see, we have 20 lines, 20 rows, that represent the 20 FD-SOI transistor of 30 nanometer of width and 40 nanometer of length that we analyze with stress condition of gate voltage equal to drain voltage equal to 1.5 voltage. On the column, we can see the different RTN bias configuration that we analyzed before and after stress of the device in order to understand how many jumps were promoted or not. In fact, the color part represents for each device and for each RTN bias configuration how many jumps I could count before the stress, so in virgin with the virgin device, and after the stress. So in green, I'm representing the cases where the number of jumps, so the number of discrete levels in my devices didn't change. In red, the cases in which the number of discrete levels decrease after the stress. And in yellow, the cases where the number of discrete levels increase after the stress. So, exploiting this particular table that summarizes all my analysis, I could achieve these two small tables. What they represent? They represent, highlighted in white, the probability to have at least one jump. Thanks to the analysis that I summarized on the table of before, we can see how different combination of drain voltage and gain voltage during my working operation promote differently discrete levels. In fact, as we can see, applying the same voltage on the drain and the same voltage on the gate during our operating condition in our MOSFET, we are able to promote most probability of RTM. Vice versa, what we can see clearly from these two figures is that more different is the voltage that we apply on our drain instead the one that we applied on our gate, less is the capability to promote RTN. So, apart from these two last conclusions, that were the main two conclusions of my work, I would like to say other two small things, confirming and corroborating what we saw in the literature. The best way to degrade a small device during our stress cycle was to have the same voltage on the gate and the same voltage on the drain. Respect, for example, having different different value of both. Another thing that we note is that devices with a really long length show a very resilient behavior. Promote stress in these devices was very difficult. And another thing that we understand is that exploiting our methodology, devices with less dimension than 30 nanometer of width and 40 nanometer of length can be analyzed because they promote too easily the breaking down. So, thanks for the attention. And
okay, thank you, Francesco. Is there any question from the jury?
The slide to the measurement setup, so one of the first slide. Yeah, exactly. This one. So if I understood correctly, your parameter analyzer is able to provide a MATLAB file, an output, yes. But what about the input voltage that you apply to the probe station? I mean, is this an automatic procedure, or for each experiment you have to set manually the testing condition?
What we did, the semiconductor parameter analyzer, in this case, is an intelligent semiconductor parameter analyzer, could be programmed also directly from the machine, but more easily from directly a MATLAB tool. So what we did was define at first which were the conditions that we would like to test, how much was the the stress time for its cycles. And yes, once it was defined and we move on with the experimentation, it promotes the voltage sweep that, yes, communicate directly with the terminal of the device thanks to the probe station.
Okay, thank you. Thank you very much. Nice job.
Okay, thank you. So let's move on to the next presentation. Andrea Gori. So Andrea Gori will present us.
Prova.
Un po' più in alto. Più in alto.
Ok. Allora. Okay, good evening to everyone. My name is Andrea, and today I'm showing you my research about a system for anomaly detection in a ball bearings using a microcontroller-based machine learning. In a nutshell, the aims of this research is to deploy a complex neural network system directly inside on a microcontroller, and we used a low-cost microcontroller and embedded MEMS sensor that is an accelerometer sensor that catches value over z-axis. Machine learning provides tool for a mathematical tool for evaluating predictions, and it provides algorithm of artificial intelligence ecosystems. And while deep learning is the stack of more than one machine learning algorithm. One of the easiest and most used algorithms in order to model complex system is the multi-layer perceptron. And it's composed by 3 main structures. And the first one is the input layers, whereas values pass through it and then reach the hidden layer 1. Here is the main core of the algorithm because it evaluates the cost function that predicts the error between the real values and the model 1 values. Then the values passes through the output layer where predictions are then evaluated, and finally everything is iterated n times, or better n epochs. This is selected by the user. Okay, in order to verify if our laboratory environment is able to deploy the neural network system, we use STM microelectronic boards with its embedded accelerometer, and we build up in at home a workbench that is composed by an electric motor from an old fan, and the board is put inside at the back of the electric motor, and it acquires accelerometer values. Then, in order to deploy our neural network, is used the Edge Impulse web platform. That is a commercial tool free of use. I remember that everything is done only to verify if our board is able to make prediction. We can see that the graphical environment of the Edge Impulse is very easy to use, and finally it's possible to build the firmware directly inside on the selected board by pushing that button. And then on the right side of the figure, we can see that it detects good, with a good probability, of course, the state of our vibrating element. The board so is able to make good and fast prediction, so it's possible to pass directly on our case study of interest. We want to study the environment of a ball bearing, in particular a rolling element of a ball bearing, but we need the real environment, but because the inability to directly operate on the real environment, emulating one is then recreated. And it's a requested device emulating vibration of a ball bearing, signals to drive that the so-called shaker, and then our board with implemented the neural network. The environment is depicted in the figure. We can see the shaker from the mothership company. It generates vibration by a specific signal, has input to the shaker. These are WAV signals format. But before implementing everything, we need to test if our embedded accelerometer is consistent with real data, accelerometer data. And indeed, in between of the shaker and the board, here is a high-quality accelerometer. We can see in the figure that the results are pretty the same, roughly the same. Indeed, we use a 200 Hertz signal to drive the shaker, and this generates, of course, vibration. If you look at the spectra signals, is the bottom figure, you can see that they are roughly in the same, depicting a peak on the 200 Hertz spectra. Then it's possible to acquire our requested signals from a previous research of Rubini and Professor Concocelli. And these are accelerometer values of a rolling element of a ball bearing. And there are three main signals. And there are the normal one, whereas no defects are present on the surface. Then the sphere mean values, where little flows are present on the surface, and the sphere max signals, where a lot of defects are present on the surface. I remember that are accelerometer values over the z-axis. Because of the length of the signals is low, 1 second, we can see in the blue figure, we need to enlarge to 10 seconds lifespan. And this is provided by using MATLAB tool. And each sample is concatenated n times, adding a white Gaussian noise to the signals. Then it's converted to WAV format. And then we can see the LabVIEW step. So in order to drive our shaker, an input signal is requested, and we use LabVIEW. Thanks to the upper left control knob, we are able to select from the 3 different conditions. The first one is the int, that is the normal state. The second one is sphere mil, that represent low defects on the surface, and then sphere max. It's important to know that because of our shakers need 1 volt as input signal, we need to normalize the values, and then it's possible to drive the shaker. Acquired signals are depicted in the figure. Look at the spectra, it's a bottom figure, and they are pretty the same. The green one is the sphere max original signal, and the blue one is the sphere max signal acquired by the shaker, moving by accelerometer while the shaker is moving. And the spectra are roughly the same. Of course, there's some mechanical offset because of the environment is fixed with screws, and this results in some mechanical offset. Okay, after having acquired the signals, it's possible to deploy and test our neural network. Collected value over that are accelerometer over z-axis are then collected in a trained data set, and that is fed to the neural network core. A multi-layer per second algorithm is used. In particular, I want to remind that we use 500 neurons, and we trained on about 160 epochs. Then we can see that the confusion matrix depicted, and we have roughly 60%, 65% of predictions good. I remember that only one feature is used in order to train the neural network. And the output layer is of 2 neurons because 2 target labels are selected, the normal one state and the fault state. Okay, finally, we can see the flow chart of our code. We can gather accelerometer values thanks to the embedded accelerometer, store inside on array, and then here is the core function of the entire firmware system, because here predictions are made. And finally, so thanks to the 2 LEDs, 2 LED presence on the board, they are turned off or turned on depending on the state. We have 2 states, the normal states and the fault states. In particular, we can see that the detection of the states is pretty good, and normal one is detected well with a probability of roughly 60%. Spheramine is predicted with a probability of 55–58%, and then Spheramax with a high probability of 70%. I remind that Spheramine values, accelerometer values, are never trained to the neural network. So this results that our network is robust. And in particular, it predicts a condition that is never trained. Once again, we used a low-cost microcontroller. And in particular with a low-cost embedded accelerometer. And I want to remind once again that the algorithm is never trained with Spheramine values. So this is a presentation of a high-complex neural network system developed at the edge. And it's possible to improve by, for example, enlarge the training data set, collect some features, and using different algorithms, for example, convolution neural network, and some other algorithm present in literature. Grazie per il tempo.
Well, it's not a gift.
Sì, of course.
Okay, questions from the jury? Any question, Roberto? No curiosity at all? I have curiosity actually.
Yes.
This confusion matrix that you showed, can you explain in 30 seconds how it's built?
We train the neural network with input values as feature, and in particular we use in particular we use the Spheramine values and Spheramax values. TensorFlow is the library we use to deploy the neural network, and finally it's possible to print this confusion matrix. The confusion matrix depicts the prediction of our test dataset, and so here is we can see that predicted label normal are really normal values. Here we can see that fault, he has predicted fault, but in reality there are normal values.
Okay, yeah. It was difficult to labels from. Okay, thank you. Any other curiosity? None, so...
Thank you very much.
Thank you. And we move on to the next candidate, Alberto Luppi.
Prova? Okay.
Okay, very good. So here you have the title in Italian, but you probably have the one in English on your slides, so let's read that one. Okay, ESP32 and MAX 86 150 smartwatch prototype to innovate biomedical wearable technology. Okay, thank you, please.
Good afternoon, I'm Alberto Lupi, and I'm going to present my work of thesis, an SP32 and MAX 86150 smartwatch prototype to innovate biomedical wearable technology. This project has been hosted by a startup in Modena called VST. The general outline of this project is characterized by a short introduction with motivation and objectives, a description of the signals involved during the examination, and a system overview. Then all information about the tests that are performed will be given, and finally a result discussion with conclusions and future improvement will be provided. This prototype has been realized in order to meet modern medicine needs and where health monitoring systems are personalized on patient needs. And also it wants to provide a new innovative idea to VST to realize a new type of product and contribute to study vital signals obtained from the wrist because they actually use hands in order to do it. The general objective of this project is the development of a device able to measure PPG and ECG signals, and in order to do it, it is necessary to connect a cheap smartwatch, the Lily-Gotti watch, with a sensor, MAX 86150, that could provide the possibility to measure these two types of signals. In order to do it, it is necessary also to verify that this connection not affect the operation of the sensor that are just installed on the smartwatch board. Photoplethysmography is a non-invasive technology that is used to collect information about the blood circulation. For this type of project, the reflectance pulse oximeter configuration has been implied. The light will be emitted by 2 or more LED, and it will be reflected by the finger. And the light that is backscattered is catched by photodetectors. On MAX 86150, that is the sensor, 2 types of LED are implemented, the red one and the infrared one. And as it's possible to see from the absorption spectrograph, the 2 type of LED, the 2 type of hemoglobin, which behavior is represented with the red and blue line, absorbs light on different way. The PPG waveform is constituted usually by the systolic peak, a diastolic peak, and the dichrotic notch. For what concerns the electrocardiography, is a widely used process used to evaluate the state of health of human heart. The ECG morphology is composed by several peaks, named with letters that go from P to T, complex segments and the interval that are used to make health diagnosis. In order to integrate this type of process on a wearable device, it is necessary to move from the usual 12 leads ECG towards a simpler one, a single lead ECG. For this project, the first lead has been chosen, so the one that uses the 2 hands. As it's possible to see from the image on the right, the signal obtained from the single lead ECG, it is just a little bit noisy than the 12 leads ECG that is represented with the red line, but both of signals show this all ECG waveform components. The system is mainly composed by 3 parts: the MAX 86150 board that has been realized in collaboration with VST, the smartwatch that implements the ESP32 microcontroller, and the computer that is used to collect data. Initially, the communication between the smartwatch and the computer are totally entrusted to your technology in order to ensure the correctness of the transmission. Then the communication are entrusted to a Bluetooth serial port profile in order to avoid physical connection, but a drawback needs to be accepted. And this drawback is that the communication speed needs to be decreased. The communication to and from MAX 86150 module and the smartwatch are totally entrusted to the Quadro-C communication protocol. As it's possible to see from the image, SDA, SCL, and the interrupt pin require all a pull-up resistor. But this purple resistor needs to be just implemented on the smartwatch board because an external implementation could cause some short circuit that could damage the device. In order to perform in order to perform the data analysis using VST standard, it is necessary to take some precautions about the rooms where tests will be performed and about activities that need to be done or avoided during or before measurements. Another important thing is the trial position. The subject needs to sit in a comfortable position with legs uncrossed and feet flat on the floor. Arms need to rest on the table at the earth level, ensuring the dipole, so the two hands don't need to touch each other during the test. The subject is also invited to apply a low pressure with the left wrist on the table in order to ensure the contact between the HEG plate that is installed on the bottom part of the smartwatch and the wrist. For what concerns the finger position, it is necessary that the index finger and the middle finger will be placed respectively on the sensor and on the other HEG plate. Here we have the front end of the software that is used to collect data. It is a software that has been created especially for this type of application. And this software allows also a first evaluation of the quality of the signal. In the top part, we have the PPG signal, and in the lower part, the HEG one. Tests are performed on 10 different subjects that are equally divided between male and female. Their age is between 20 and 30 years old. And another parameter that is used is the BMI that need to be lower than 25, and it is used to to give information about the state of health of the person that want to do this type of test. On each subject are performed 6 different tests, and each test have different settings about PPG. So the pulse amplitude and the pulse width will vary. And looking at the HEG, we have a different total gain that are obtained configuring registers. Looking at the test 1 and test 2, they show the same gain, but obtained using different configuration of the register in order to see if this change could affect the final result. The data analysis has been performed using 3 different parameters. Signal to noise ratio, where the useful signal is the peak valley amplitude of the sample signal. The signal saturation that need to be avoided during the test. And the statistical evaluation that is performed using a novel methodology that allow to say if a data is statistically significant looking at its p-value that need to be lower than 0.5. And also to KHSD test. VST use the box plot function in order to provide us information, and in order to better understand how it works, it is necessary to compare it with the probability density function of a normal distribution. As it's possible to see, the 50% of data is between the first and the third quantile, and the median line it is used in order to evaluate the signal to noise ratio that has been multiplied by 10,000 in order to allow a better visualization. Looking test result about the HEG, it is possible to see that the first and the second test show more or less the same signal to noise ratio. And looking the result of the 2K HSD test that are reported on the table on the right, the p-value is more or less equal to 1, the one that compared the first and the second test. So these 2 tests are they appear to be the same. Looking at test 4, test 5, and test 6, they have the same value of gain. They appear to have the same signal to noise ratio as expected. The PPG signal, the ER1 and the red one, show an high variability in data on both results. And this could be motivated by the fact that the PPG signal could be affected by various factors, as the pressure of the finger on the sensor and also the finger position on it. About conclusion of this project, it is possible to say that every subject needs different configuration of the MAX 86-150 sensor. The finger pressure and also its positioning could affect some results. And the initial hypothesis about the communication between Lily-Gotti watch and the MAX 86-150 providing HEG and PPG signals turned out to be possible. For future improvement, it is necessary to improve usability, implement smartwatch function using the sensors that are just on the smartwatch board, and using with the hardware and mechanical improvements and preliminary signal-to-noise examination, it is possible to increase the quality of the signal that this prototype could provide. And considering the data collected and good performances obtained with this prototype, this project has solid basis to continue. Thanks for the attention. Here I have my prototype.
Okay, very nice. So show it to the jury, please. Okay, any question for the candidate? Please, Matthew.
So in one slide, you show the body mass index, the BMI.
A BMI, yeah.
So the question is, were you planning to find some correlations between signal statistics and the BMI?
Yeah, in my thesis I reported some reasoning about it, because if the BMI is too large, maybe the subject could have a little layer of fat on finger that could affect the final results. So it is necessary to take into account also this index, because it is necessary to have more or less the same BMI to have more or less the same configuration of the finger that is used to collect data.
So some calibration may be required, maybe?
No, because this type of project is just to see if this communication is possible, because I start this project without know if it could be possible or not. So it is just the first step of the project.
Okay, thank you.
Okay, thank you. Any other question? Alessandro, okay. We have to return the prototype, I guess. So I don't know where it is, but...
BST want it, so...
Please, where is it? Okay, good. Okay, thank you then, please. Okay, now we have our next chat. Okay, Simone, can you hear us?
Yes.
Okay, let me see if you are allowed to share.
I cannot share the screen for the moment.
You cannot share, so we have to go here.
Okay.
I guess. And yeah. Is it? Come on. Simone.
Yeah, now I can share.
Can you try again? Now it should be possible.
Yes.
Okay.
Okay, can you see it?
Yes, please put everything in full screen mode. And yes, title of your thesis is firmware development of active safety functions for industrial trucks compliant with the EN ISO 13849 and EN 1175 standards. So please, Simone, stage is yours.
Okay, so first of all, good afternoon. I am Simone Maiocchi, and I'm going to present my thesis project, which regards the firmware development of active safety functions for industrial trucks complying with EN ISO 13849 and EN 1175 standards. Now, first of all, this thesis is the result of an internship carried out in Zappi company, which deals with the production of motor controllers for different types of applications in reality. But the main one, and the one that will be considered in this thesis, is that of industrial trucks. In particular, the development of industrial trucks is affected by European functional safety standards. And one of them, the EN 1175, as we will see, has been recently updated. The goal of this thesis is to update the standard software, the so-called Zappi standard, in order to make it compliant to these newly updated European standards. Now, we have talked about functional safety standards, but first of all, what is functional safety? It is basically the part of a system which is related to the detection of a potentially dangerous condition, resulting in the action of some protective mechanism or protective device, basically with the task to bring the system in a safe state. In many fields of application, and industrial trucks is one of them, functional safety is a legal requirement which is regulated by two different types of standards. We have generic functional safety standards, which provide the methods and processes for a correct design flow. And the one of interest for us is the ISO 13849. And then we have instead technical standards, which instead refer to a specific type of product. And the technical standard of reference for industrial trucks is the EN 1175. Now, regarding ISO 13849, there is a section which is specifically dedicated to software development, which specifies which should be the software life cycle to be followed. In particular, it is the so-called V model depicted here in figure, and circled in red, we have the steps that have been developed during this thesis. So basically, starting from a list of high-level requirements, an architecture able to satisfy those requirements has been designed, architecture which is modular in the sense that it is divided into modules which have a well-defined logical tasks. The modules have then, of course, been coded, and then we pass to the testing part, the testing phase, which has been carried out in an incremental way, in the sense that we started by testing the modules independently, and then integrated between them and with hardware, and tested all together. Besides of this, other qualitative coding measures are requested, which instead are more technical. EN 1175 is instead the technical standard of reference for industrial trucks, and it defines all the safety functions that have to be implemented. So basically it defines some dangerous conditions, and if one of those conditions occurs, the system, so the truck, must be brought in a safe state. Of course, the standard defines also which is the safe state. This standard has been recently updated, specifying much more safety functions in much more detail than before, and it will be fully informed from 2023. The goal is so to update our Zappi standard in order to make it compliant to this newly updated standard. Which is the problem in doing that? The problem is that the standard software is a very large software, full of features, developed in more than 20 years, and so rethinking it from the scratch was not feasible. For this reason, it was decided to create a safety layer, which is built as an extension of the standard software and so runs in parallel with it, with the goal to ensure the compliance to functional safety standards. What this safety layer will do is so essentially to validate all the set points for the different actuators of the truck, so traction motors, pump motors, valves, and so on. And moreover, it can take actions in order to bring the truck in a safe state. For example, activating an electromechanical brake or removing the enable from some actuator and so on. Now, coming to the requirements, in particular regarding hardware, the software shall be compatible with AC2 and ACX controllers, which are double micro induction motors controllers, which can work both in dual or combi and wired or can open configurations. Dual means that we have two traction motors, one for the right wheel and one for the left wheel, while in combi we have one motor for the traction and one motor for an AC pump. Moreover, in both the configurations, we can have other hydraulics actuators, basically for the load handling system. So in the development, we have to take into account all the possible configurations: dual wired, dual can open, combi wired, or combi can open. Other requirements are, of course, all the requirements from ISO 13849, so models, modular architecture, and so on. Regarding the requirements from EN 1175, we concentrated on 3 sections: 2 regarding the traction of the truck, in particular uncontrolled acceleration from standstill and uncontrolled behavior while truck is moving, both with reference to the particular case of the inner wheel of the truck, and then the whole section regarding the safety of the load handling system. Moreover, some internal requirements have to be satisfied, which are added by the company, for example, regarding timing requirements, so the duration of the main loop of the microcontrollers, but also others that, of course, have to be satisfied. Now, coming to the part regarding the safety of the traction, we have that the EN 1175 always refers to the truck as a whole. So you will never see in the standard the concepts of inner and outer wheel, because it always refers to track speed, track acceleration, and so on. However, while steering, inner and outer wheel can have different speeds, of course, due to the electronic differential. That's because the outer wheel will in general define a higher radius with respect to the center of the curve, and so in order to have slip-free steering, it will have a higher speed. So the question is how to adapt the requirements about the traction to the case of the inner wheel. The answer is that, well, regarding uncontrolled acceleration from standstill, that's not a problem, because we can treat the 2 wheels in an independent and separate way. Regarding instead uncontrolled behavior while truck is moving, it is a little bit more complicated, and that's because we have to take into account the dynamics of the steering. Here, an example is reported. This is just a qualitative plot of a situation that can happen. So here at some point we brake, and while braking, we also steer. What happens is that between T0 and T1, even if we are braking, the speed of the internal wheel is increasing. And so in this transient, the only information that you have that has to be respected is that the speed of the internal wheel must remain below the speed of the outer wheel. Moreover, this is just a situation that can happen, and so that's not trivial. However, at the end, by considering different factors, in particular not only the speed of the inner wheel, but also the motor torque and the steering ratio between the 2 wheels, it has been created a diagnosis which is able to differentiate the situations and satisfy the requirements. Now, regarding the load handling system, we have that the firmware development must not only be compliant to the standard, of course, but also must work on different applications. And that's not trivial, because the load handling system can be controlled by different functions, so different inputs, for example, to lift the load, to lower the load, and so on. And these functions are carried out by different actuators, so different outputs, for example, AC pump, DC pump, proportional or digital valves. However, the relation between input and output, so between the function and actuator, is not defined by a standard, is not on a priori, because it is application dependent. It depends on the hydraulic system of the particular truck we are considering. So how to deal with all this? And this is the architecture proposed, where the blue ones are basically the modules that have been implemented. So we have, first of all, an input-output interface, which takes as input all the information about the relation between input and output of particular track we are considering, and allows so to achieve the generalization capability that we need. Then we have 2 modules, analog signals elaboration and movement request validation, basically for input processing. 1 module for operator presence detection, and then the path is sort of split in 2, one for the AC pump and one for all the other DC outputs. For both, we have a forward control, which is related to the generation of a safe set point for a given output, and the backward control, which is instead related to the check of the feedback in order to understand if the safe set point is correctly being actuated. The outputs of the architecture are basically all the safe set points for the outputs, and possible alarms, where with possible alarm we of course also mean the handling of the reactions to that alarm. Now, ended the design phase, of course, there is the need to pass to the test phase, starting from purely software test. First of all the modules have been analyzed with a static code analysis tool with the goal to eliminate any possible stylistic error and standardize the software. So a lint script has been run on all the modules. Lint is basically a software tool for static code analysis, and a report with all the errors has been generated. The stylistic errors have been then, of course, been corrected and eliminated. Then all the modules have been unit tested. The unit tests are particular tests with the goal to test the modules independently from each other and to improve general software quality. They are carried out with a black box approach, which means that given a set of inputs, we verify that the output of the module is the one to expect, and they have to be designed in the sense that there is not a given script. They are based in few words on some mock files in which you feed the modules with a given combination of inputs, you tell which output you expect, and it is verified that the output, the real output, is the one that you expect. At the end, a report containing all the tests performed has been generated. Finally, integration tests, which are carried out on software integrated with hardware in order to verify that the safety functions required by the standard are correctly implemented. They have been carried out not on real trucks, but on a bench, on motors connected to a flywheel. And in order to read the variables of interest, some debug messages are sent to the external CAN and plotted with the CAN Analyzer tool. Moreover, a password-protected procedure has been created in order to modify some variables in the code via CAN and basically simulate fault conditions so that to carry out the test. Here we see an example of a report of a test carried out on the internal wheel. So what happens is that at some point we brake, so the set points of the two wheels are set to 0. However, the speed of the internal wheel, which is the black one in the first plot, does not go to 0, but accelerates more in the negative direction. And we can see it also from the current, which is in the first plot, which is basically proportional to the torque, which is trying to push the motor toward even higher negative speeds. That's, of course, not the right behavior, and for this reason, after 400 milliseconds, which is the reaction time, an alarm is set, and what happens is that the H bridge of the motor is deactivated, so we are no more able to provide torque to the motor. We also activate an electromechanical brake, and so the motor will just brake due to the friction of the electromechanical brake. Now, coming to the conclusion, we achieved full compliance with ISO 13849 due to all the documentation produced during the development process. The results for the tests performed are in agreement with the requirements of the updated version of the EN 1175. All the internal requirements have been satisfied, and we also achieved the goal to design a general purpose software that can be implemented for all the applications, for all the trucks, using AC2 or ACX ZAPI controllers. Thanks for the presentation, and thank you.
Okay, thank you very much, Simone. Is there any question from the jury for you? No questions. Just a curiosity on my side. Can you hear me? Yes.
Yes.
Okay. You basically implemented the safety layer in software, right?
Yes.
In the end, you were able to fulfill all the requirements, but did you ever find a critical situation where the software was delaying the operations or in a way that could become maybe critical in some other prototype or in some other implementation, or was the software layer, the delay of the software layer introduced always negligible, and we should just not bother about it?
It is negligible, also because, of course, the detection of dangerous conditions is not something that should be always instantaneous. The standard defines some times, so some tolerance times that should be respected. But at the end, these times have been respected, so that was not a problem.
Okay, thank you very much. Then, thank you again.
Thank you.
Okay, so we should now switch again to okay, is that working? Okay, very good. Maybe you want to repeat the title because actually the mic was switched off when I read it.
Okay.
Okay, please.
It's on the first slide. So. Prova? Okay. Hello everyone and good afternoon. I'm Alessandro Mattioli and my thesis is about the active power factor correction using a Vienna rectifier. And I developed this project while I was working at Altran with the knowledge that I acquired during my traineeship. So we were asked in the first place to do this side of a system because we had to supply a complex object, and it was required to convert the input three-phase coming from an avionic power supply to a DC value that, as we will see later, will be 350 volts. And all that while keeping the power factor and the total harmonic distortion at the minimum level possible. So, okay. The following presentation will be divided into 6 main sections. I will first talk about the requirements, then I will show the building block of the 2 boards that I developed, and then the PCB. Then I will talk about the control algorithm. I show you the simulation results, and finally the conclusion and the possible future improvements. So regarding the requirement, as I said, the power supply is an avionic power supply, so it works at 115 volts with a frequency of 400 to 800 hertz. The output voltage of the system should be 350 volts with a possible fluctuation of plus minus 10 volts, and the output power should be around 350 watts. The total harmonic distortion when the absorption is 350 watts should be lower or equal to 7%, and the power factor should be larger or equal to 0.98. Also, this system needs to be able to work when the absorption is only 15 watts, needs to be able to work when one phase is missing, and also when the power supply is at 90 or 130 volts, which are 2 abnormal situations that may happen. So this is the building block of the first board, which is the power electronic board that contains the Vienna rectifier. On the left, we have the input connector where the 3-phase will enter. Then we have the Vienna rectifier, which is the side of the circuit that will modulate the input current and the output voltage. And then we have these elements here, which is the gate controller that will control the MOSFETs inside the Vienna rectifier. And the other 3 blocks are used to sample the input current, input voltage, and output voltage. All this data coming from these 3 elements are analog voltage and will be sent to another board, which is the control board, thanks to the connector on the bottom. This is the simplified schematic of a Vienna rectifier, and in this project, the input inductance cell is 1 millihenry, and the output capacitance is 6 microfarad for half the output voltage, because the Vienna rectifier will provide 350 volts, but providing plus 175 and minus 175 respect to the ground, which is also virtually clamped to the central point of the output, which is M. This is the PCB that I developed for the project, and it's a 4-layer PCB that I designed on Altium Designer. And as we can see on the bottom side, we have all the sensing circuit, and these are separated from the top side that contains the Vienna rectifier, and the Vienna rectifier is the most likelihood source of noise. So I try to isolate as much as possible the two sides of the circuit. In this case, a very important point was to keep the trace sufficiently large to let the current flow through them, and also the distance between the traces, as the voltage is relatively large, and we want to avoid any electronic breakout because of an electric arc. This is the other board, which is the control board. In this case, we have the input connector that comes from the previous board. It provides plus 175 volts, and the first block is a flyback controller used to generate plus 12 volts isolated from the primary. And this side of the circuit is an inverting back boost converter used to generate the minus 12 volts. And using these two supply used by the OP amp and other side of the circuit, it's possible to supply the remaining part, which are some ADCs used to sample the analog voltage coming from the previous board. The result then go into a microcontroller that will implement the control algorithm, and it will generate the PWM that will then be fed into the gate controller that will control the Vienna rectifier. The control algorithm contains two main loops. The first one is the outer control loops and is used to regulate the output voltage. So it does the difference between the output voltage and the reference output voltage. This difference goes into a proportional integration controller, and the output is the so-called power reference. Then from the power reference, we obtain the current reference that will then be fed into the inner control loop that I will show you in the next slide. And at this point, the reference current should be the same as the real input current, and the remaining part I used to obtain the DC corresponding current starting from the AC input current, and the last part is the transfer function of the load. This is the inner control loop instead, so we have the difference between the real input current and the reference input current. The difference goes into a proportional controller, and at this point some other terms have been added to reduce the third harmonic effect on the total harmonic distortion, and also thanks to this term it's possible to obtain a transfer function which is time invariant and is more easily controllable and easy to study. Then the result is fed into the Vienna rectifier, which is represented by the plant model in this scheme. So this is the first simulation of the circuit, and in this case we can see how the system behaves at 115 volts with a frequency of 400 Hertz. And in this case we can see some variation on the output, and these are due to the load that changes between 15 watts to 350 watts. As we can see, the power factor is 0.997 here, when the absorption is 350 watts, and the total harmonic distortion is 6.6%. In the abnormal situation instead, so 90 volts, we have that the power factor is still very high because it's 0.996, but the total harmonic distortion in this case is much larger because it's 12.2%, and the output voltage has some fluctuation also in this case because of the changes on the load. In this other situation instead, as we can see, the power factor is lower, and it is 0.983, with a total harmonic distortion of 17%, and the output voltage also in this case has some fluctuation, but only due to the changes on the load. And finally, to conclude, we have the case of the one-phase loss. So in this case, the phase C was not fed into the circuit, so only two phases were used. The power factor is still relatively large because it's 0.981. The total harmonic distortion is much larger, of course, and the output voltage has some fluctuation, but this is because we have 350 watts of absorption, while the power density and the input is much lower because one phase is completely missing. So for the conclusion, as we have seen, the system has achieved a power factor of 0.98 with a total harmonic distortion of less than 7%, and the output voltage has always remained into the limits of its fluctuation. Also, the system has been stable when the absorption was only 15 watts in the two abnormal situation and also when one phase was missing. For the possible future improvement, we can say that using an adaptive controller can provide better results, especially when the absorption is only 15 watts. And also increasing the input inductance up to 5 millihenry is possible to reduce the total harmonic distortion down to 2 to 3%, depending on the frequency. And an output capacitance of 50 microfarad can keep the output voltage within the limits of its fluctuation, also when one phase was missing. So thanks for your attention, and I hope you appreciate it. Thank you.
Thank you very much.
Thank you.
Any question? No? Everything clear? Roberto, fully satisfied? No question at all.
Okay.
Well then.
Thank you. If you want, I have.
Of course, you
I have printed
should
the
you should
PCB,
always
so if you
show
want- okay.
the prototypes. Of course. Okay, thank you. Okay, so now we have candidate Luca Monduzzi Donazzi. Please come to the stage. And the title of the thesis is Estimation of the Degree of Wear and Predictive Maintenance. Is that right? Okay, very good. Ooh. Try to open again. Maybe. Do you have your PC or? Okay, here it is. Please.
Okay. Good afternoon. The title of my thesis is Service Brace of an Agricultural Tractor, Estimation of the Degree of Wear and Predictive Maintenance. This thesis work is carried out at the CNH Industrial, and the objective of this thesis is the implementation of a method for estimating and diagnosing the degree of wear of the service brace for do the predictive maintenance. The outline, so the summary of this presentation is the following. First of all, I would like to speak of the predictive maintenance, so what is the predictive maintenance and what are the advantages of the use of the predictive maintenance. Then I would like to present how the service brakes work, and then I would like to present the method that I have found for estimating the degree of wear, and I would like to present the diagnosis logic that I have developed for estimate the degree of wear, and then in conclusion I would like to show you the conclusion and what are, in my opinion, the future development of this thesis. Maintenance is a key aspect for automotive application for on-road and off-road vehicle. If we don't do the maintenance, we know that sooner or later components or system break down or failure, and a breakdown or a failure, in particular in the agricultural tractor, leads to an increase of cost and problem of safety for the driver. There are three different maintenance approaches that we can see in this slide, that are the reactive maintenance, the preventive maintenance, and the predictive maintenance. For this thesis, I use the predictive maintenance. In the case of the predictive maintenance, the maintenance is performed just before that the failure occurs, so thanks to the sensor and the control unit of the component, it's possible to know in real time the status of the component, and then it's possible to do the maintenance just before that the failure occurs. So
So the advantages of the use of the predictive maintenance are the possibility to the maximization of the useful life of the component, the possibility to prevent the occurrence of unexpected failure, the possibility to planning in advance the maintenance intervents. So in this way it's possible to increase the efficiency and reduce the downtime of the machinery. And then the other important advantages of the use of the predictive maintenance is the possibility to reduce the cost. Okay. Now I want to show you how the service brakes work, and when the driver inside the cabin press the brake pedal, the piston, that is one of the part of the service brakes, go in contact with the disc, and so the tractor decelerates and then the tractor stops to move. The service brakes wear because that there is a wear of the friction material. The two methods, now I want to show you the two methods that I have found for estimate the degree of wear of the service brakes. I have found the method that uses the Lauree model, where this method is found in literature, and then the second method is related to the monitoring of the average power and energy dissipated in a single braking. And I have found this method experimentally, so I have analyzed data related to the service brakes, and then I have decided to use this method. Now I want to show you in the detail these two methods. The first method, that is the use of the Lauree model, where thanks to the Lauree formula it's possible to calculate, so it's possible to know the total work volume material. And for calculate the total work volume material, it is necessary to do a product between a constant K and the energy dissipated in all the braking. The constant K is a constant that we can find experimentally. And if you use this method, what I expected is that if there is an increase of the total work volume material, it's expected that there is an increase of the degree of wear. So in practice, this method is based on the calculation of the total work volume material. And for calculate the total work volume material, it is necessary to know the braking torque, the speed of the wheel, and then as consequence the instantaneous power and the energy dissipated. So in practice, for calculate the total work volume material, it is necessary to know the energy dissipated in all the braking. And for know the energy dissipated in all the braking, it is necessary to do a sum between the energy dissipated in all the previous braking and the energy dissipated in the current braking. And for know the energy dissipated in the current braking, it is necessary to know the instantaneous power, and then for calculate the instantaneous power, it is necessary to do a product between the speed of the wheel and the braking torque. For know the value of the speed of the wheel, there is no problem, because that inside the tractor there is a sensor that measures the speed. But the problem is related to the braking torque, because that the question is, how can I get the braking torque? Because that the number of sensors available inside the tractor is limited. So there is no sensor that measures the braking torque. And for solve this problem, thanks to the use of the experimental test, so thanks to the use of braking test, it was possible to create a torque pressure curve, where thanks to this curve, if I know the brake pressure, as consequence it's possible to know the braking torque. And in the case of my tractor, there is a sensor that measures the brake pressure, and then thanks to this curve, it's possible to know the braking torque, and then it's possible to calculate the energy dissipated, and then as consequence, it's possible to know the total work volume material. Okay, this one is the first method, and the second method that I have found is related to the monitoring of the average power and energy dissipated in a single braking. I have decided to use this method because inside the control unit of the tractor there is a table that records the value of the average power and energy dissipated in a single braking. And I have analyzed this table for a tractor where the service brakes are wear. And I have observed that this tractor have done braking at anomalous value of average power and energy dissipated. So for this reason, I have decided to create a logic that counts how many times the average power and energy dissipated in a single braking exceed certain critical threshold value. So in practice, I create a logic that counts how many times the table of the average power and energy dissipated is populated in the red region when the tractor brakes. If I use this method, what I expected is that if there is an increase of the count, so if there is an increase of the times that average power and energy dissipated in a single braking exceed the critical threshold limit, is expected that there is an increase of the degree of wear. Then I decided to use this method, so to present this method for estimate the degree of wear, because that with this method for estimate the degree of wear, I take into account not only the energy dissipated, like in the case of the Lauree model, but I take into account also the average power dissipated. And then for calculate the average power dissipated, I do a ratio between the energy dissipated and the breaking time. So in this case, with this method, I take into account also the breaking time that can depend on the driver and on the braking condition and on the field. Okay, so this one is the second method that I have presented, and now I want to show you the diagnosis logic that I have developed, and I have developed two diagnosis logic. The first diagnosis logic is related to the use of the Lauree model, and the other logic is related to the monitoring of the average power and energy dissipated in a single braking. The first logic that I want to present is the diagnostic logic based on the use of the Lauree model. This logic is divided into two parts. The first part is represented by this state flow block that is used for calculate the total volume material. And now I want to show you a simulation that I have done in the simulating environment. And the signal on the bottom that is called enable is a signal that became 1 when the braking end. So in practice, this signal is used for count the number of braking, and the signal on the top is a signal that is related to the estimated total volume material. And from this simulation, it's possible to see that if the number of braking increases, there is an increase of the estimated total volume material. And this one is what's expected, and then this one is what the Lauree model say in practice. But in any case, now I want to continue with the presentation of the diagnosis logic based on the use of the Lauree model. Now I want to show you the second part of the diagnosis, that is the true diagnosis, where in practice the final diagnosis of the degree of wear is based on the check if the total volume material exceeds a certain limit. And the outcome of this diagnosis can be healthy, so the service brakes are in good state, fault in progress, so the service brakes are at the 50% of down life, or faulty, so the service brakes are wear. And so this one is the first diagnosis logic. Now I want to show you the second diagnosis logic that is related to the monitoring of the average power and energy dissipated in a single braking. Also in this case, this logic is divided in two parts. The first part is represented by this state flow block that is used for calculating the average power and energy dissipated in each single braking. And then the second part of the logic, that is the true diagnosis, is composed by this block, where inside this block happens a comparison, so each average power and energy dissipated in a single braking are compared with some threshold value, and the output of this logic of this block is a variable count, where the variable count is a variable that counts how many times the average power and energy dissipated exceed the critical threshold value. So in practice, the variable count increases of 1 if the average power and energy dissipated exceed the critical threshold value. And then the final diagnosis of the degree of wear is based on the check if the variable count exceeds a certain limit, and if this variable exceeds a certain limit, it means that the service brakes are wear. Okay, so this one is the second diagnosis logic, and now I want to show you the conclusion and what are, in my opinion, the future development of this thesis. In conclusion, during this thesis work, I have found two possible methods for estimating the degree of wear of the service brakes, and with the use of simple calculation and simple diagnosis logic, it's possible to obtain the degree of wear of the service brakes, and the diagnosis of the service brakes can be obtained following daily action, that is the engage of the service brakes. And in my opinion, the future development of this thesis are, first of all, do experimental tests and analysis to better identify the threshold value to insert inside the diagnosis logic, and then in future it's better to validate and compare the two diagnosis logic that I have present in this presentation. But at the end, I can say that during the thesis work, satisfactory results are obtained, and that justify an investment of researches for future development. Okay, this one is all, and thanks for the attention.
Thank you very much, Luca. Questions from the jury? None? Actually, I have a curiosity about your work. You mentioned several times the energy and the average power, okay, as key metrics for all your work.
Okay.
Now, a recurrent issue in reliability wear-out type of problems is whether the average is the most meaningful quantity, or whether we should also look at peak values. You might have situations where the peak is very large.
Because we have observed that the peak value can be not a good condition indicator for estimate the status of the service place. So for this reason, we have decided to analyze only the average value.
But could it be a good indicator of the triggering of major faults in the braking system? I mean, maybe the average wear out is okay, but then, I don't know. I'm just guessing because I'm not a mechanical engineer, but a crack develops somewhere because of an intense braking power, and which does not correspond to a large average.
So
is that anything that is reported in the literature that you found, or?
No, honestly, this I have found this method see data, so tests that are available by the company, by the CNH, but obviously this one is a first study, so this one is an initial studies of how the service brakes work and how it's possible to detect this work with the sensors that are available. So in future it's better to verify this hypothesis and then observe other things, but this one is only a initial study.
Okay. Very good. Thank you very much for your presentation. Okay, so we are actually quite on time, and in spite of some technical difficulty, the next presenter is Mattia Tosi. Mattia, could you please come to the stage? For you as well, I only have the Italian title, so you may want to read the title in English.
Can you hear me properly? Can you hear me? Okay, so good afternoon, everyone. My name is Mattia Tosi, and today I'm going to talk about a possible implementation of a DC motor drive on a modified three-phase inverter for roadway applications. I would start by thanking my thesis advisor, Professor Bianchini, for his support during my internship. And before starting with my presentation, I would like to spend a couple of words about the company I've been working with in the last 6 months. This company is called Leitner, and it's a worldwide company. It's actually an Italian company from South Tyrol, and they design ropeways and wind turbines, and they are actually one of the leaders in designing ropeways. So the goal of my thesis, as the title suggests, is finding possible circuit solutions for obtaining a DC converter for ropeways by modifying an already existing three-phase AC inverter, which Leitner manufactured, and it's been operational since 2010, more or less. I would like to start now with the contents of my presentation, and I will start with a brief introduction, and then, as I said, since my work is about finding modifications from an already existing converter, I will talk and give you a few details about the Leitner's frequency converter. And then I will talk about the DC motor I've considered for my work of thesis. And then I will show you the two designs I've made for this DC converter, this possible DC converter, and I called them the 3-phase design and the 2-phase design. And later you will clearly recognize why I called them in this way. Then I will show you the Simulink models I've made so far, together with their simulations, and then I will end up with some conclusions. So in order to start, I would like to first answer to these 3 main questions. What was my work about is the main question, is the first question. My work, as I said, was about modifying an existing converter for ropeways and making it suitable for driving DC motors. Why the need of this work? Well, this comes from Leitner's desire to manufacture their own DC converter because actually they are buying third-party thyristors converters from third-party manufacturers company. And nowadays, today, they want to build their own converter, and so they want to find possible implementations for this converter. Where is my work going to be operational? In particular, in Italy, there are several ropeways which are still making use of DC motors. And I'm saying still because nowadays new installations have AC motors, induction machines, for example, but still several plants are making use of DC motors. This is the Leitner's frequency converter that you see on the left, actually on the right. And it has a power, it's a cabinet mount converter. Inside we have all the electronic circuitry and components. It has a power up to 250 kilowatts with possible parallelization. So this means that ideally we can reach any level of power that we need for the plant by putting in parallel more cabinets working together. It's an AC to AC converter up to now, and it's designed for ropeways and wind turbines applications. And this converter also allows the motor to work in 4 quadrants of operation. So this means that we can work with positive and negative speed and positive and negative torque. Going into details of this converter, it is composed, as you see in the block diagram in the upper picture, it's composed of 2 main stages. They are the so-called AFE and inverter stages. The AFE stands for active front end, so it means that it takes care of the grid side and rectifies the grid voltages, while the inverter stage is on the machine side. And especially the inverter was the part I was focused on because it's the part that I had to modify to find the best solution for driving DC motor, because the motor now is changing. Before it was designed for AC motors, but now I have to take into account a new type of motor. In between the AFE and the inverter, we have a DC ring capacitor that you will see in a better way in the next slide. This converter has the capability of bidirectionality. So it means that the energy flow can go either from grid side to the motor side or vice versa, from motor side to the grid side. In the lower picture, you can see some of the driver boards which are used for driving the IGBTs. The IGBTs in particular, they compose the AFE and inverter stages. So we have 6 IGBTs each per stage, and they are controlled with PWM control signals. And then we have on the grid side and on the machine side, we have the filtering stages. And in between, as I said previously, we have the DC ring capacitor for maintaining a stable voltage. So the part that I had to modify was the inverters. And the AFE instead is completely okay, like it is working now. The DC motor I was considering for my work of thesis is a 500 kilowatts of power DC motor. The pictures on the right are actually not the motor. They are not motors from Leitner's plant, but they are just to give you an idea about the sizes of a 500 kilowatts power motor. It's a brushed motor, so it means that we have, as you see in the pictures, we have a commutator where the brushes are in contact. And it has a separate excitation circuit, and it also allows field weakening. Since I said that it has a separate excitation. We have two different circuits when we look at the equivalent electrical circuit of the motor. And as you can see, we have the flux or excitation circuit and the armature circuit. The windings of the motor are modeled as the equivalent inductances, and then we also take into account the Joule losses with equivalent resistances. And also, we have an additional contribution, which is the back EMF voltage, which is induced due to the rotation of the motor. Now I will start by showing you the first design I was thinking of, and I called it the three-phase design. Why three-phase? Three-phase because the idea is to use all the three phases of the inverter stage for supplying the motor armature circuit. And by connecting together the phases, then we reach the motor. We also see a capacitor at the output, which is used for smoothing the voltages. And for the excitation circuit instead, since we are already employing all the three phases for the armature circuit, we need an additional hardware, an additional circuit. And in this case, it's an H-bridge circuit. Why an H-bridge? We need an H-bridge because if you look at the armature control circuit, we are not able to supply a negative voltage to the armature of the motor. So if we want to reverse the rotation of the motor, we need a circuit able to reverse at least the flux in this case. So the idea was using an H-bridge circuit that, depending on the IGBT's configuration, we can reverse the voltage of the stator. What are the pros and cons of this design? The pros are that we have acceptable power losses on IGBTs, that the inductor and capacitor components are easy to design. I simply applied, for example, buck converter formulas. And the cons instead are that from the ripple constraints, we get bulky and expensive passive components, so inductors and capacitors. And this translates into the need of designing a new cabinet. And this is a con because it will be better for the company to have the same cabinet, not needing to build a new one. And also another con is that we need an additional hardware, so the H-bridge. And this means that we also have to find space for it inside the cabinet as well. So the idea was to find another design, and I called it the two-phase design. Because in this case, we are not employing three phases as before, but only two phases for supplying the armature of the motor. And what's new is also that the sizes of the inductors that you see in the picture and the capacitor are halved. Why this? What's the trick behind this design? Well, the trick is the use of interleaving. Because if we use interleaving on the PWM control signals of the IGBTs, we are able to obtain, after the combination of the two legs, we are able to obtain a ripple which combines in a destructive way. And therefore, we can also have smaller passive components on the legs. What does interleaving mean? I already anticipate a little bit, but in this simulation that I carried out, you can see in the first two rows that I took the upper IGBT's control signals. And as you see, they are phase shifted of 180 degrees. In these two rows, we have the currents per each leg, the yellow one and the blue one. And you see, just imagine the amount of ripple we have here. Okay, just keep in mind this amount of ripple. What instead we have after the combination of the legs, we have this current, the green one. So as you can see, we get a smaller ripple, and now I will show you how much is smaller. And then also we get a doubled frequency of the ripple. Doubled frequency means that we can halve the sizes of the passive components like inductors and capacitances. So the ripple in the legs is about 42 amps, while the ripple going to the motor is 18 amps, and the reduction is 57%. The two-phase design has also, of course, a new circuit for the excitation, because the idea is, since we are only employing two phases for the armature, then we have one unused phase remained. And so this unused phase is used for the excitation this time. We have an half-bridge circuit configuration. And also, an additional thing is that we're using solid-state relay. This solid-state relay allow to, as before was doing the H-bridge circuit, they allow to reverse the polarization of the excitation circuit. What are the pros and cons of this design? The pros, a big pro, is that it fits in the same cabinet. So it means saving money for the company. The inductors and capacitors are, again, easy to design. Reuse of inductor. What does this mean? This means that Leitner was already using another inductor for another application, a DC-DC converter application. And this inductor, we know that it fits in the cabinet because now it's inside the cabinet for this other application. And we did the test, and this inductor is perfectly working also with this design and with this application as well. So reusing also this component is, again, another pro for the company because you don't need to order new components to make new study. You have already all the tests and everything you need. No additional hardware required. We don't need the H-bridge circuit this time. What are the cons? The only con I found until now is that there's the need to implement the interleaving in the firmware of the cabinet. Talking about the Simulink models, these are the ones I've created, and this picture is the common main view for both the two designs in Simulink. We have a main block, which is the DC-DC converters block, where we have all the control circuitry. This is quite a huge Simulink model with different layers. We have the input block, where we can define the simulation conditions. And then we have the motor block, where I implemented, as you see in the pictures on the right, I implemented the mathematical equations of a DC motor. So as we can see, the DC-DC converter block is simply taking as output the DC link voltage. Why the DC link voltage? Because I didn't need to modify the AFE stage I was talking before. So I started from the DC link voltage. The control circuitry is taking this voltage and giving as output the voltages needed for supplying the DC motor. Inside the control circuitry, we see, for example, two PI current controllers, one speed controller, and then we have some blocks that generates the duty cycle, and then we generate from the duty cycle the PWM signals for the IGBTs. And these PWM signals will then be sent to this block, which is, for example, here I took the two-phase inverter, so we have only two legs for the inverter. Now I want to put in comparison the two designs. This is the three-phase design, and on the right you have the two-phase design. As you can see, it's quite noticeable how we have here three inductors. We are using three phases, we connect them together, and then we go to the motor. On the other design, we only have two legs, and then also you see in that picture the output capacitance. Here you don't see the capacitors because it's in another subsystem. So I simulated the same driving cycle for both the models. And this is not, in blue you can see the mechanical speed, and in red the load torque, of course. This is not a real world, let's say, behavior for a rope wave, because as you see, the load torque is suddenly stepped up to half of the nominal load torque. But this was just for showing you how the system is working correctly, because we see a short decrease in the speed when we suddenly apply a certain load torque, and then the system keeps following the reference I wanted to simulate. I reach a speed higher than the nominal speed. In this case is equal to 1.2 in normalized values. And what happens inside the PI controller? We see it on the right. We have the blue, which is the measured current, and the red is the current reference of the controller. And as you can see, when we apply suddenly this step in the load torque, we see that also the reference steps up for counterbalancing this sudden increase. Here in this picture, I put in comparison the two designs in terms of currents and torques. And in green, you see the current going to the motor. In blue, you see the torque. And what you can immediately see from the current is the difference in terms of ripple. So here we have in the three-phase design, we have a much larger ripple than in the two-phase design. And this is due because of interleaving, as I was saying before. So I calculated the ripples, and we have a ripple reduction of 85% if we use interleaving. So stepping back to the conclusions, the two models are both valid and they work as expected. Of course, a trade-off between functionalities and cost had to be found. The reasonings, for example, whether to use the same cabinet or designing a new one, take bigger components or use other components. A first prototype, as I know, will be built soon, and it will be based on the two-phase design with interleaving. And also I know that the firmware for this prototype is currently under development. Thank you very much for your attention.
Okay, very good. So, last one, questions, curiosities? A bit tired, a lot, but it was clear, very clear.
Thank you very much.
No, actually, the presentation was very good.
Thank you very much.
So, is this going to become a product, you think?
Yes,
of
very,
Lightner?
very soon.
For sure, yes?
Yes, yes.
Okay, when?
Actually, in May, the components are coming. For example, the capacitances, because the company didn't have these capacitors, and also the inductors, because they have to order more inductors.
Okay, more, but of the same type.
Yeah, exactly. But because nowadays there is quite a huge problem in deliveries, so yeah, it's a bit of a problem. But in May, June, the first prototype will be built.
And what was the main reason for Lightner to have its own design?
It's
not just cost reduction, having it own
not
made,
only.
or?
I think working with them, I understood that they want to be involved 100% when they deliver a ropeway plant. So they don't want third-party manufacturer, because when there is a problem, you need to call them.
Parts for the operation of
the maintenance is everything done. They are trying to reach this politic, let's say, of maintenance.
Can we expect a reduction in the ticket for the ropeway?
I don't think so.
Okay, very good. Thank you again.
Thank you very much.
Okay, so this ends the presentation part. Now the jury will discuss about the final marks. So we will reconvene at about 5:30 p.m. Okay, for the actual proclamation or okay of the, and actually there will be together with the proclamation also the assignment of 4 prizes for former students of ours. That's a prize that is offered by Fondazione Morlini, and you will hear more about that during the presentation. Okay, so the results will be given, and maybe if we are too much, we will have to ask first the master degree students and parents, and then the laureate degree students and parents to enter the room separately. But we will see when we are all here. Okay? So let's reconvene. The industrial advisors, I think there are maybe 1 or 2, are welcome to stay with us and to bring their testimony on the students. Ci siamo tutti quanti? Allora, buonasera, benvenuti di nuovo. Iniziamo questa piccola cerimonia finale con la presentazione di un premio. Abbiamo il piacere di avere con noi il dottor Toscano della Fondazione Lauree Morlini, che offre un premio di laurea per degli studenti particolarmente meritevoli. Presidente, grazie di essere con noi questa sera e le lascio il microfono per qualche parola di introduzione e di spiegazione sulla origine di questo premio e sulle sue motivazioni.
Buonasera a tutti, io rappresento la Fondazione Lauree Morlini che per una volontà della mamma le è scomparsa molto giovane, era un ingegnere elettronico e quindi la volontà della mamma era quella di, avendo una sola figlia, di costituire una fondazione, dando dei premi a ragazzi meritevoli che potevano portare avanti il nome della propria figlia. Per cui vi ringrazio a tutti, soprattutto ai ragazzi che hanno...
Bene. Il premio, ricordiamo che è assegnato a studenti di laurea, di laurea triennale in elettronica che hanno deciso di proseguire i loro studi nella magistrale, d'accordo? Ed è assegnato sulla base di un insieme di fattori che, se vuole dire lei prego, ma che comprendono sia diciamo il curriculum durante la laurea triennale che la parte di curriculum durante la laurea magistrale intrapresa nel frattempo fino a una certa data che, se non ricordo male, è il 31 luglio, giusto, del 2021. Va bene, allora io direi che cominciamo chiamando appunto qui a ricevere il premio i 4 studenti, a partire da Mattia Andreani. Prego.
Della fondazione.
Prego, se vuole, può far vedere, guarda, c'è il fotografo anche. Ah no, ok. Prego, beh, un applauso facciamoglielo a questi studenti. Ok, proseguiamo con Lisa Tondelli. Abbiamo poi Jacopo Nicolini. E infine Amerlelio Kelly. Bene. Ragazzi, se volete venire, così fate una foto di gruppo con il presidente della fondazione, la commissione. Questo dai piedi, prego.
Ok, stringiamoci.
Stringiamoci, siamo fuori da...
Meglio?
Ancora di più? Siamo in seconda fila.
Sì, mettiamo la seconda fila.
Benissimo. Grazie, complimenti a tutti. Bene, adesso passiamo alla proclamazione dei risultati degli studenti di laurea triennale. Ok, un attimo che devo trovare, eccolo qua, il mio foglietto. Allora, bene. Allora, Inizio chiamando qui Lorenzo Benatti. Lorenzo Benatti. Allora, signor Benatti, la Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato la sua prova finale, ha approvato il suo esame di laurea con il punteggio di 92 su 110. E pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me oggi delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Signor Bizzi, Jonathan, anche per lei, signor Bizzi, la Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato la sua prova finale, ha approvato il suo esame di laurea con il punteggio di 108 su 110. E pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università e me oggi delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Signor Andrea Comastri. Buonasera, signor Comastri. La Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato la sua prova finale, ha approvato il suo esame di laurea con il punteggio di 110 su 110 e lode. E pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me oggi delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Signor Luca De Bartolo. Signor De Bartolo, buonasera. Anche per lei la Commissione ha preso atto del curriculum degli studi e dopo aver valutato la prova finale ha approvato il suo esame di laurea con il punteggio di 94 su 110 e pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Signor Francesco Laudato. Signor Laudato, la Commissione ha preso atto del suo curriculum degli studi e dopo aver anche valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 87 su 110 e pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Signor Marco Mura. Signor Mura, la Commissione ha preso atto del curriculum, del suo curriculum degli studi, dopo aver valutato la sua prova finale, ha approvato il suo esame di laurea con la votazione di 109 su 110 e pertanto per i poteri conferiti dalla legge al magnifico rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Signor Federico Rovighi. Signor Rovighi, la Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato anche l'esito della prova finale, ha approvato il suo esame di laurea con il punteggio di 108 su 110 e pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Infine, signorina Lisa Sarego. Anche Per lei la Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato l'esito della prova finale, ha approvato il suo esame di laurea con la votazione, con il punteggio di 106 su 110. E pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università e a me delegati, la dichiaro e proclamo dottoressa in ingegneria elettronica. Bene, con questo abbiamo terminato la prima parte, c'è la proclamazione dei laureati triennali. Proseguiamo con la proclamazione dei laureati magistrali. Allora, chiamo qui il signor Alex Aglietta. Signor Alex Aglietta, la Commissione ha preso atto del curriculum dei suoi studi, ha valutato il suo lavoro di tesi e ha approvato il suo esame di laurea con il punteggio di 94 su 110 e pertanto, per i poteri conferiti dalla legge al rettore di questa università e me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Qui adesso abbiamo il primo dei laureati a distanza, li facciamo, esatto, li facciamo come ultimi, va bene, i ragazzi mi stanno sentendo credo, quindi dovrebbero essere consapevoli di questo. Aspetta che accendiamo anche, qui c'era la telecamera spenta. Allora, signor Elias Said Fezel. Signor Fezel, la Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il lavoro di tesi ha approvato il suo esame di laurea con il punteggio di 108 su 110 e pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Signor Francesco Gammarota. Signor Gammarota, la Commissione ha preso atto del curriculum degli studi, ha valutato il suo lavoro di tesi e ha approvato il suo esame di laurea con il punteggio di 95 su 110 e pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Signor Andrea Gori. Signor Gori, la Commissione ha preso atto del curriculum dei suoi studi, ha valutato il suo lavoro di tesi e ha approvato il suo esame di laurea con il punteggio di 96 su 110 e pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università, a me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Signor Alberto Luppi. Signor Luppi, la Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato il lavoro di tesi, ha approvato il suo esame di laurea con il punteggio di 104 su 110 e pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Proseguiamo adesso con il signor Alessandro Mattioli. Signor Mattioli, la Commissione ha preso atto del curriculum degli studi, ha valutato il suo lavoro di tesi e ha approvato il suo esame di laurea con il punteggio di 110 su 110 e lode. E pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Signor Luca Monduzzi Donassi. Signor Monduzzi Donazzi, la Commissione ha preso atto del curriculum degli studi, ha valutato il lavoro di tesi, ha approvato il suo esame di laurea con il punteggio di 110 su 110 e pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Signor Mattia Tosi. Ok, anche per lei la Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato il suo lavoro di tesi, ha approvato il suo esame di laurea con il punteggio di 108 su 110 e pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Adesso abbiamo la proclamazione degli ultimi due candidati di oggi che sono connessi via Teams. Prego entrambi di accendere le telecamere in modo tale che anche il pubblico qui li possa vedere. Signor Maiocchi, la vediamo. Ecco, signor Mohamed Ali. Allora, signor Mohamed Ali, la Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato il suo lavoro di tesi, ha approvato il suo esame di laurea con il punteggio di 82 su 110 e pertanto, per i poteri conferiti dalla legge al magnifico rettore di questa università e a me oggi delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Okay. Mohamed Ali?
Yeah.
Okay. Sorry, okay. Should I repeat the proclamation in English? Did you get...
Thank you. Thank you very much.
That was okay? Okay. Best wishes.
Okay, thank you. Bye.
Bye bye. E infine il signor Simone Maiocchi. Buonasera, la Commissione ha preso atto del curriculum dei suoi studi, dopo aver valutato anche il suo lavoro di tesi, ha approvato il suo esame di laurea con il punteggio di 110 su 110 e lode. Conferiti dalla legge al magnifico rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in ingegneria elettronica. Bene, direi che siamo arrivati ormai quasi alla fine di questa cerimonia. C'è da festeggiare per tanti, anche per noi docenti che vediamo a compimento un percorso lungo di questi ragazzi. Soltanto due parole diciamo di carattere generale che riserviamo comunque sempre per questo tipo di occasioni. Innanzitutto un ringraziamento a questi ragazzi per l'impegno che hanno messo nei loro studi, nelle loro tesi, nei loro progetti, nei loro esami. Un ringraziamento alle famiglie che li hanno sostenuti e che li hanno supportati. È estremamente importante questo. Siamo profondamente convinti che una società moderna, una società che voglia aspirare a un certo livello di benessere, di condivisione di questo benessere, non possa prescindere da dar valore all'istruzione superiore e lo debba fare tutti i giorni supportando e sostenendo i propri giovani nella ricerca di un lavoro entusiasmante, di un lavoro professionalmente soddisfacente, di un lavoro soddisfacente e anzi accattivante dal punto di vista anche personale. Per questo tutti quanti dobbiamo contribuire a creare un clima favorevole e un clima positivo. Ne sentiamo più che mai la necessità in questi giorni in cui siamo confrontati quotidianamente con cose che non avremmo mai voluto vedere in Europa o al confine con l'Europa da decenni ormai. Quindi, cosa altro dire? Abbiamo come corpo docente, abbiamo la responsabilità. Ci impegniamo a mantenere questo corso di studi aggiornato. Si tratta di discipline che ogni giorno cambiano, che ogni 5 anni presentano significative novità, a formare dei ragazzi che siano in contatto e che conoscano da presto anche le realtà aziendali del territorio e non solo. Oggi abbiamo visto anche creati e costruiti in collaborazione con aziende, anche in collaborazione con grandi aziende internazionali o con dare per scontato, perché sono comunque un asset importante di studi e della formazione che cerchiamo di trasmettergli. Un altro asset molto importante che sapete, questi ragazzi hanno affrontato uno shock ulteriore, diciamo, nel passaggio tra triennale alla magistrale, quello di dover cambiare la lingua insegnamento, la lingua di apprendimento, la lingua nella quale si esprimono dal punto di vista tecnico. Hanno passato un test quindi più significativo di altri, nel quale però noi crediamo molto, perché fare ingegneria oggi, ingegneria di punta, senza avere una padronanza della lingua inglese sta diventando veramente molto difficile, se non impossibile. E quindi siamo certi che questo sforzo in più che gli abbiamo chiesto sarà ampiamente ripagato. Oggi è una giornata di festa, non la faccio lunga, vi lascio ai vostri festeggiamenti. Non dimentichiamoci comunque che questa storia del Covid non è mica ancora finita, quindi magari cerchiamo di contenere, e ci sono anche altre cerimonie, altre lauree in giro, quindi le esplosioni più significative di gioia magari lasciamole quando siete un pochino più distribuiti su un'area un po' più vasta. Grazie a tutti, grazie ancora, complimenti ai vostri ragazzi, i migliori auguri per loro, la loro carriera, e a voi come famiglie per la soddisfazione che senz'altro vi daranno nel futuro. Grazie. Un ringraziamento un'ultima volta alla Fondazione Morlini per i premi che ha offerto, che sono un'altra concreta testimonianza di una realtà della realtà civile di questo paese, che crede e che investe in istruzione superiore. Grazie.